Hello, this is what I hope will be a fairly short video just to talk about something which I don't think is very well represented on YouTube in any other videos, and that is this series of, at the time, kind of revolutionary portable oscilloscopes put out by Tektronix in the 70s and 80s. This is a model 212. But there was actually a lineup of these, all with the same case design and appearance, but slightly different feature sets and capabilities. The series started with the 211, which I believe came out like in 72 or 73. I haven't been able to find anything absolutely definitive on that. But certainly in the earlier part of the 1970s, the 211 was a single channel scope, and you had knobs just like this, with the upper knob being the volts per division or vertical selector, and the lower knob being the horizontal sweep selector, or period per horizontal division selector, if you will. Then there was the 212, which had similar specs, but it was a two-channel device, and that caused the two vertical selectors to be here, color-coded dark gray and beige, and then they moved the horizontal selector back here. The 213 was basically just like the 211. It was a single channel, but they figured it was going to be used a lot as a multimeter, and it was not only a scope, it was also a digital multimeter. So they still had the knobs for vertical and horizontal, but they moved them to the front, and you could adjust them like this. And then right along here was a set of buttons, with the top button being the digital multimeter button, which changed it from being a scope to a digital multimeter. And then below that were the function selections for the multimeter, such as volts, amps. Actually, I'm not sure if it did amps, come to think of it, but certainly volts, AC and DC, ohms, that type of thing. It may have had amps too, I just don't recall. When it was in digital multimeter mode, it had a custom set of ICs inside, which would use the horizontal and vertical deflections of the CRT to actually paint the numbers, to actually spell out, 1.02 volts, for example. And it was kind of cool that you could actually use any of the selections here to be the vertical displacement when you were in oscilloscope mode. So instead of just volts per time, as a normal oscilloscope would do, you could have it be, amps over time or ohms over time, for example, which was pretty cool. And I don't know if anybody else had anything like that. Anyway, beyond the 213 was the 214, and I'm pretty sure that was the digital storage version of this. Basically, it looked just like this 212, but it had the digital storage CRT in it, and another set of smaller buttons along here, which were partially for control of the storage mode. And that was, they had a special type of phosphor and an erase plate, or however the technology worked. I don't remember exactly anymore. But the phosphor and the CRT were set up in such a way that once the image was painted, the phosphor continued to glow. And there was some sort of a refresh update, and you could erase it and so on. But at least for a fairly short amount of time, you could capture a one-time sweep, trigger it once, sweep the electron beam across, and the CRT would just remember it and continue to display it. But over time, the longer you waited, it kind of got more fogged out and vague looking. But, for something that wasn't a digital scope and didn't have anything really expensive in it, that was kind of amazing. And then there was the 221, which I think was the newest one, and also the highest one in the series. And that was just like the old 211. It was a single channel scope, but it had, I believe, a higher bandwidth and some other features that were a little newer and or nicer than the 211. As I mentioned earlier, the Model 212 came out in the early 1970s. I found several sources online that give slightly different dates. I think it's pretty well established that the 214, which is the storage model, came out in 1973. I would presume this being a simpler one that it might have been slightly earlier, but I don't think it was any earlier than the beginning of the 1970s. I've also heard that this series, the 200 series, was a joint collaboration between Tektronix and Sony, at least as far as the design went. I'm not sure if that was true. I've also heard that about a later and full-size series of scopes that actually said like Tektronix Sony or Sony Tektronix or something on them. This says nothing of the sort, so that may have been specious information. So at this point I sort of discount the Sony aspect of this unless I hear more authoritatively that they were involved somehow. Anyway, so the 212, and I think most of the ones in this series were not very high bandwidth. I think they're only, this one's 500 megahertz, and you know, it's not a speed demon, but it was plenty good enough for the types of applications it was intended for, mostly like a laboratory technician or a field service person. The build quality is quite good, although I wouldn't say it's as good as the Tektronix, you know, laboratory or bench oscilloscopes. It's still a high quality piece of gear, a nice solid case. It's got the fold away kickstand on it, and it also has these two hangers here. You could put a neck strap around your neck and hook them onto here, and then hang it on around your neck so it's hanging right in front of your chest, and all you had to do is look down and the screen would be right below your chin, and you could easily reach the controls, and also hold test leads with both hands, for example, or you know, be manipulating trim pots or something else on whatever you're testing while the scope is right there in front of you without needing a table or something for it, which is a big plus. So let's look at the rest of this thing. Again, the design is perfectly conventional. I still need to clean this up a little bit. You can see some dust and crud built up on the selectors. But anyway, you've got your 2 channels of volts per division selector. And if you've selected an external horizontal input, then the gray knob becomes the amplitude adjust for that. You've got an external trigger, which you can put in a banana jack. You can plug in a jack to connect the common of the scope to a circuit common. You've got your sweep adjust here, just like on any oscilloscope. And here you've got your 2 channels of selection. They're identical. There's a calibration controls you can access with a small screwdriver. But you've got your usual AC, DC, and ground input coupling for both channels. You've got the position control. And if you don't want one of the channels to be working, you just turn its associated position control fully counterclockwise, and that turns that channel off. So you could have this behave, for example, as a 1-channel oscilloscope instead of a 2-channel, and any channel you want could be turned off. And then you've got your variable volts per division control. If you've got it turned fully clockwise, then it's in the calibrated settings selected by the knobs up here, but otherwise you can adjust it freely with the small knobs. Then you've got your horizontal magnification control and your horizontal position control. There's also focus. It's not done with a knob here. You have to put a screwdriver in. Power switch. The trigger sources are a little bit unconventional. On a normal scope, you would have, for example, here's my analog scope, or bench analog scope. You could select channel 1 or channel 2 as the triggering source, or line frequency or an externally applied triggering signal. On here, you don't have all those options. You could put it in comp, in which case it actually selects the trigger signal from the signal being applied to the vertical deflection amplifiers after channels 1 and 2 have been merged by alternating or chopping between the two. So it's not channel 1, it's actually channel 1 and channel 2 combined, which is sort of weird. I think that could come in handy for some things, but I don't recall ever using it myself. I recall when I used these, I always treated channel 1 as if it was channel 2, made channel 2 my primary channel, leave the switch in the middle position, and thereby be triggering off of what I was mentally thinking of as channel 2, or thinking of as channel 1. So in that sense, that's perfectly conventional, or you can select the external trigger. There's an auto preset, which, see if I can get the light. If you turn the triggering level knob fully counterclockwise, it has a predetermined level it's looking for that it just selects for the triggering set point, or you can move the knob away from full counterclockwise and select your own trigger point. And if you're in the left half, everything to the counterclockwise of the 12 o'clock position, you're selecting a position on the rising slope of the waveform. And if you're moving the knob to the right of the 12 o'clock position, then you're selecting a point on the falling slope of the waveform. So let's see, is there much more to the controls than that? I don't think so. One cool thing is that you've got built-in test lead storage. By just wrapping them up around the body of the scope here, they fall into these slots, and the rubber is kind of dried out here, but normally, let's see if I can get it up, this rubber barrier would kind of help hold the leads in and protect them. And this area here where there's no barrier coming around the corner, I've got all my leads clipped together here, but this is basically what they look like, kind of a pistol grip looking lead, and those are designed to fit right here around this corner. So the long part is here and the short part is here, and they just snap into those positions. So there's absolutely nothing about the leads or the clips on the ends, the probes, that is exposed. It's totally tucked into the body of the scope. Similarly, around the back side is a storage place for the line cord. I've got it currently plugged into an AC supply because the NiCad batteries in here are dead. I'm waiting on some replacement ones I've ordered. And then there's a little trap door on the back where you can tuck the actual plug into to get it out of the way, and then close the little door. So let's see, you can make all your normal adjustments. Vertical and horizontal positioning, variable, got your intensity adjustment, your variable horizontal, and your horizontal position. And I think I already changed this. Yes, I did. So there really aren't any other controls, and the probes do not have a ×1 ×10 selector like most scope probes do. It's just always ×1. It is what it looks like it is. Now, I can put the horizontal into XY mode, which is down here, and you can see here now that I've got the Lissajous pattern displayed, which is the composite of the vertical and horizontal signals. I've got that arbitrary waveform on one channel, and then the sine wave on the other channel. That looks kind of cool, doesn't it? Let's see. I think I can do some looking at the manual for those who are interested in that type of thing. I think I already mentioned that I bought this from an eBay seller, which was some sort of a thrift shop, and they didn't really know what they had. They just listed it with exactly what it said on the front, 212 oscilloscope and the word Tektronix. And again, since they didn't know whether it was working or not, I made them an offer because I wasn't sure what I was going to be getting, if it was going to be junk or not. Pleasantly surprised that it turned out to be pretty good shape. Anyway, it did come with the manual. Somebody's scrawl on there. This is actually the service and instruction manual in one. Usual good Tektronix manual. Has a nice introduction, describes its basic specifications, which are, let's see, 1 millivolt to 50 volts per division in 15 steps in a 1-2-5 sequence. It's only 5% accuracy, so not exactly laboratory grade accuracy, but good enough to get basic adjustments made in the field and, you know, inspect waveforms and such. The bandwidth is DC to at least 500 kilohertz. Approximately 1 megohm input resistance. Maximum 600 volts on the inputs. It does have a chopped and an alternating mode, but you can't really select that. I believe it picks automatically depending on the horizontal settings you've specified. Let's see. Yeah, as it says there, the preset trigger level is triggered at a preset level on a positive slope of the triggering signal, and it isn't specified exactly what that is. Anyway, let's see what we've got here. It is not isolated, so the power supply line cord of this scope is not electrically isolated from the probe, so you have to make sure if you hook it up to some equipment that you're hooking it up to something which is isolated. Line voltage range is 110 to 126 volts. It does have an internal double battery pack, each of which is 5 rechargeable NiCad A cells. So 2 packs of 5, and that's just so they could fit it. I think the packs go on either side of the CRT, kind of surrounding it. Let's see, 3 to 5 hours of operation on the battery. The scope weighs 3.4 pounds. Rated to operate from +5 Fahrenheit to +131 Fahrenheit, or -15 C to +55 C. The dimensions are 3 inches high, 5 1/4 inches wide, and 8.9 inches deep. Covers the controls very succinctly. I don't know, there may have been a separate instruction manual besides this, because it does say service in here, and then just the cover says instruction manual. So there may have been a separate instruction manual that maybe went into a little more detail, but I think what's in here is perfectly adequate. This is a nice breakdown of how the scope is put together. There's one circuit board along the side here, which pretty much has all the horizontal and vertical circuitry on it. This is what a typical battery pack looks like, but there's 2 of them, one on each side of the CRT. There's a power supply board that sits along the bottom underneath the CRT, and then along the top, I'm sorry, I got it upside down. It's along the top that has one circuit board and another circuit board along the bottom. And I don't remember which one is which offhand, but one of them is the high voltage board, I believe, to drive the CRT, and the other one's the power supply board. On some other versions of the scope, for example the 213, which had the digital multimeter built in, there were actually 2 boards in a sandwich configuration here. One of them was very much like the single channel scope, and then the other board that was sandwiched with it had all the digital multimeter circuitry. And then they had not only a board on the top and a board on the bottom, but they had another board on this side, and that handled the high voltage, the power supply, and the digital character generation circuitry. There's calibration information here, which I won't get into. I wanted to go over the circuit just a little bit. There's some nice troubleshooting aids. There's a circuit description. Nice of them to do that. Some nice block diagrams, corrective maintenance, electrical parts list, but of course it's all just listing Tektronix part numbers. It doesn't mostly help you with things if you are trying to find parts after Tech doesn't support it anymore. Luckily, most of the parts, except for things like potentiometers and switches and the CRT, are parts that could probably be replaced by more generic parts. There are a couple of ICs in here which are proprietary custom ICs, and good luck trying to find replacements for those, although I do understand from various websites that there are places that have them, should you need them. Obviously all the ICs in mine are working, so I'm not too worried about that. So let's see here. This is what I'm looking for. And tech manuals are always good for this. They always have the big fold out, so you can be reading the text part and then having a diagram off to the right if it's set up that way. So the block diagram, you've got your usual direct or capacitively coupled or grounded input switch for each channel. Then you've got your voltage per division attenuators. You've got an amplifier for each channel. And then you've got your vertical second stage amplifier. It's also the channel switch, because with any single gun oscilloscope like this, it can really only display one waveform at a time, and to give the illusion of displaying 2 waveforms, it's alternating back and forth and counting on the phosphor persistence to make it look like there's 2 being displayed simultaneously. So they have a switcher circuit here that alternately turns one amp on or the other amp on, and then they are basically just they're actually coupled together with a very simple circuit, but it's almost like they're wire-ored, if you will. And then one or the other of them is always active, and they alternate back and forth. And that comes into your single vertical amplifier, which is the power stage. operates the electrostatic deflector plates. This is an electrostatic CRT, so it's doing deflection by putting higher voltage on the plates as opposed to trying to use, for example, magnetic deflection. And then you've got your external trigger, which has an attenuator, and here's your trigger source where you can pick external. You can pick the channel 2 where it's taking it straight off the channel 2 amplifier, or you can pick the composite source, which, as I mentioned before, is taking the common bus signal after the 2 vertical amplifiers, and whatever's on there is used as the source of the trigger signal. Then you've got your basic trigger circuit with the trigger level potentiometer, and if you're in XY mode, then it also taps the other channel off to come in here. You've got your seconds per division control going into the trigger circuit. Come out into your horizontal amplifier with your position control, and that operates your electrostatic plates for horizontal deflection. There's also the chopped or alternate clock circuit, which drives both the vertical mode circuit and the unblanking amplifier, which makes sure it blanks the CRT during the reverse sweep, so you don't see that on the screen. And there's really not that much more to it than that. Here are some nice pictures of what the circuit boards look like. Pretty well packed in there, but you can see here is an example of one of their proprietary ICs. Most of the other ones are very normal looking dips, and there's a good chance you could find something that would replace those if you needed to, but these other ones are probably going to be a little harder if you need to replace those. This is the back side of the same board. You can see the back side of the 3 rotary switches, the back side of all the pots, and as you would expect from Tektronix, they're all pretty nicely encapsulated, high quality pots and switches. There's some test signals. Here's the full schematic, showing just exactly the same thing, but you can see there's not a lot of components in here really for 1970s technology, and trying to squeeze all this into a small package. The circuit's actually quite simple. A minimum amount of compensation controls on the voltage selector. You've got a balanced pair of, or a matched pair of FETs on the input stage. And that's acting as a front end to a single op amp, which is your first stage vertical amplifier. And you also add your DC balance in there. And you can see here that it couples the first order 1, 2, 5, 10, 20, and 50 into one gang, and then the 0.1, 0.2, 0.5, 1, 2, and 5, these are grouped into the various compensation circuits, and then within those you have your resistor ladder here on the other side of the op amp, which is giving you your intermediate selections. So you basically get your conformed vertical signal coming out of here, same thing coming out of here, and let's see. Here's your triggering circuit. Very simple, just a flip-flop and a transistor and a few resistors, some diode logic, and here are your 2 second stage vertical amplifiers, each one taking the signal from the first stage and adding the variable volts per division and also the position control mixed in. Same thing for the other channel here. And then you can see the outputs of these are actually tied right together with each other. This is your hardwired mixture, but this is not a regular amplifier. It's got a control signal which clearly turns on and turns off the output of the amplifier, and those are driven off these 2 signals which are directly off the two outputs of the flip-flop. So the flip-flop is going back and forth and can only turn on one or the other of these op-amp output stages, so they can be directly wired together and then go directly out to the vertical amplifier for the power stage to the deflection plates. So a really simple circuit, only 4 op-amps, and essentially 4 transistors do the whole thing. Some more test waveforms. And then here's your horizontal section. 4 gangs on the horizontal seconds per division selector switch. This circuit, I think, is a proprietary circuit in what looks like a 16-pin DIP IC. Takes care of pretty much everything in one chip. There's hardly any of the other components, just a few switches and resistors taking care of that whole thing. The blanking circuit is derived with a transistor, and there's a couple extra support components, but not a lot more to it than that. Then you've got your high voltage section, which on this isn't very high. The maximum voltage is only 65 volts required for deflection, so a very simple and direct circuit using a double differential output op-amp. Your vertical gain, your horizontal position, your horizontal gain, everything goes into that. And then you've got your push-pull or complementary stages here going to the deflection plates, and also the unblanking signal. And that's what the horizontal board, or I'm sorry, this is the power supply board. And what is this? What am I looking at? Yeah, it's the power supply board. And then finally, here is the part of the circuit that handles CRT support functions. So there's a voltage multiplier circuit here using capacitors and diodes. And this is the higher voltage necessary to accelerate the electron beam through the CRT. Not really sure offhand what voltage it gets up to here. I don't see where it really says, but I imagine it's higher than 65 volts used for the deflection. Anyway, pretty simple circuit. There's not even any transformers in there. It's all just done with this fairly simple and compact circuit. And there is a electronic trace rotation, which I hadn't mentioned before. I don't think you can access it from the outside. I think you have to pop the case. I don't recall seeing... Yeah, I don't see it on the outside. I think you actually have to take the case open to get at it. You're not supposed to have to do it very much, but it does have the winding around the CRT for trace rotation, and it can be adjusted. And then here's the power supply. It's a transformerless power supply, and this is why I mentioned earlier it's not isolated from the AC line. You just come in with your line cord, you've got a fuse, and then you've got basically a simple RC filter circuit with a dual winding choke on both the hot and neutral sides of the incoming line. Resistors and capacitors tied together here with the center tied through an RC network to circuit ground. And then your power switches over here, and it comes back, and you apply that incoming AC to this diode bridge, and you get your, roughly, I'm actually not sure what the voltage should be here, but I don't imagine it's much more than 12 volts, because, well, let's see, no, I suppose at least 15 volts, right, because 10 NiCads in series have to be charged, so the voltage has to be higher than that. And that's coming directly off the plus side of the diode bridge, straight into the batteries. Couldn't be simpler. So you may ask, how come we're not applying rectified 120 volts to the batteries. Well, that's because you don't come directly into this side of the AC side of the diode bridge. You have to go through this circuit here, and when the power switch is open, you go through a pretty high value resistor here, 150K, and then that is applied to this. So you have a large drop through that resistor when the power switch is open, and that's used to keep the batteries trickle charged. So you get a lot of voltage drop right here. And obviously they have it calculated so you get an appropriate voltage at this point. Now when you actually turn the power switch on, it shorts out this circuit with this circuit, and it still has 150 ohms, but you can see in both cases the resistor is paralleled by a capacitor, and the capacitor values are different, 1.7 microfarads versus 3.3 microfarads. So it's actually not dropping that much of the voltage operationally speaking through the resistor. It's dropping it through the capacitive reactance. And that's a pretty common technique. So you get more of a drop this way and less of a drop when you're going through a closed power switch. Anyway, so that's how they get their voltage dropping without the bulk and weight of a transformer. Then you got your battery circuit here, and when you actually turn the power switch on, now you're presumed to be running off either the line or the battery, but it's the same node in the circuit. Goes through this other half, the power switch, and has a Zener diode here and your LED. It's set up in such a way that when you're running off the line or a fully charged battery, the LED is on bright. If you're running on the battery alone, the LED will drop out when it gets to a critical voltage level. So when you see your LED wink away on you, you know your batteries are nearly dead and you should turn off the scope or plug it in. And then you've got a fairly straightforward voltage regulator circuit here through two transistors and another Zener diode. And then you've got all your other voltages derived here with this transformer, which is quite a small transformer in here. It's running at a fairly high frequency. These two transistors here in a push-pull stage energize whatever voltage you're getting out of the regulated voltage up here from this power supply circuit. You're going to one side or the other of the primary coil, and then the one side or the other is being turned on and off very quickly to sort of simulate an AC input. And then there's a feedback from that through this small coil to drive the transistors, so it gets a nice stable oscillation and the circuit works the way it should. Then you've got a very straightforward secondary winding here with a diode bridge and filter capacitors. That gives you your plus and minus 5.6 volts. Based on the small capacitor value, it's clearly not pulling a lot of current out of there. It doesn't need to. Nothing in this circuit needs it. Then there's another winding which has a half-wave bridge and a choke, and this is providing your 69 volts for the deflection circuits. There's no regulation there to speak of. And then tapped into the same circuit is your high voltage divider circuit, which is really the high voltage boost circuit I mentioned earlier, which is for the electronic beam acceleration. Comes off of that same winding. And then finally there's a small winding over here which gives you approximately 0.6 volts for the heater on the CRT. So just like any other CRT, it's a vacuum tube and it needs to have a heater element. So that's the whole circuit. Again, very simple for an oscilloscope, but it does its job. And then there's all the parts identifiers for the exploded component view. Here we go, exploded component view. So there's your case bottom. your CRT, and there's a nice illustration of the two 5-cell battery packs sitting on either side of the narrow part of the CRT. Item 32. Which is your high voltage amplifier circuit board, is sitting up on top of the CRT. And item 48, which is your power supply circuit board, is on the bottom. And then you've got your everything else circuit board, your vertical and horizontal control circuits and amplifiers are all on this one very compact board. To me, that's the most amazing part of this, that they could get everything you basically need to run a scope except for the high voltage section on that one board, at least half of which is taken up by the physical bulk of all the knobs and switches. Slide switches, 1, 2, 3, 4, 5, 6 slide switches, 3 rotary switches, 8 potentiometers which are full size, plus another 1, 2, 3, 4, 5, 6, 7 or so trim potentiometers, all on that one board. And then they still managed to squeeze in a place to wrap up your probes and your power cord and get it into this small package. Really quite a remarkable scope for the time. And I hope this one keeps running for a long time, although really to me it's just a nostalgia item that I don't need to have working, but it's sure nice to have it working. So I hope you found this video interesting.